Okay, I rewrite the head loss. That was what we initially did for the junction. We identify all the components, including the junction and the friction, and the head loss due to the friction at both pipes. And for the junction, we're using this formulation, and we only need to find the K factor based on what type of junction we have, which can be found from the table in the textbook. And also, we need to calculate the velocity for each component. For the first 3 junction, we use velocity v1, and for the last one, we use v2. V1 and V2 are the velocity, and they can easily be calculated using the mass flow rate and the area. Then we calculate the head loss due to the friction in the first pipe. So the first pipe has a velocity 10 meters per second and also the diameter of 100 millimeters. So it means these lengths including 10 meter plus this length plus this length. The other parameter we need to find was the F factor, which can be found from the Moody diagram. We're going to do the same for the second pipe. So we need to find the Reynolds number, which is the velocity times diameter divided by viscosity. The velocity is 2.5, the diameter is 0.2, and viscosity, that's the value for the viscosity of the water. Give us the Reynolds number approximately is about 510 times 10 power 5. And the other parameter we need is the relative roughness for the second pipe. So it's 0.2 divided by 200, and the relative roughness will be about 0.001. Using these both parameters, we can find the F value from the chart. The F value will be about 0.0205, and now we can put all of them here and find the HL2. So if I just replace them, the length is 10 meters, this is the length, divided by the diameter, 0.2, times 2.5 squared divided by 2 times 9.81, and the final value will be about 0.32652 meters. So that's the head loss for the second pipe. And it's interesting to see how the value for the second pipe is much smaller compared to the first part. And it's obvious because the length of the first part is much longer than the second part, and also the velocity is much smaller. So for the second part of the question, we need to find the H. H is the difference between the height in first reservoir and the second reservoir. So how are we going to calculate it? How are we going to find it? Using the energy equation. So if you write down the energy equation, we have the kinetic energy, that's the component for the kinetic energy, the pressure, and plus Z2 minus Z1 plus HL. The most important step is how we're going to simplify this equation. Okay, it's obvious this term goes 0 because we don't have any pump or turbine in the system. The second term is also 0. The velocity here and here assume is 0, and the reason we assume is 0 because it's a reservoir. So it's a big tank and the flow is almost stationary. The pressure is also 0 because at both points is atmospheric pressure. This parameter we're looking to find it, and HL is the head loss. So if I rearrange this equation, it's going to be Z1 minus Z2 will be HL, which is the H is equal to HL. So HL is the total head loss, so it means the summation of all components. We individually calculate the head loss of them. If I put all of them together, the final answer for the head loss will be about 50.79 meters. So it simply means initially the height at the tank at the first tank is higher than the second tank, and but the reason they are not in the same height because we have a head loss in the system. If there is no head loss, we expect that they remain in the same level, but because the head loss, due to the head loss including the junction and also the friction, the height at the second reservoir gonna be lower than the first one.